So we will do start with the two programs today. The first program we'll be doing is addition of two 32-bit numbers. Assuming that numbers are stored assuming that numbers are stored in the code memory. So we know that there are two ways I can store the numbers in the code memory. One is at the time of writing the program, I can store the numbers in the code memory. Either at the end of the program, one method, or in between at the beginning of a program, I can store it. So let's store the numbers in the code memory. DCD means defining in the code memory or allocating in the code memory double words, in a sense 32-bit number. So DCD means allocate 32-bit numbers for storing number 1, that is a 10, for storing another number called 20. So total memory allocated for these two numbers will be now 32. That is a 4 bytes, another 4 bytes. So at the nums, you have a 10. At the nums plus 3, because nums is the starting address of the memory allocated for this one. Nums plus 3 is what? The address of the memory location where 20 is stored, because 4 bytes is required for each of the numbers. Like this comma, I can store any number of numbers. Also, I can have one more label. I can have one more label and say DCD, I can store the numbers. Like this, we can allocate the numbers in the code memory. Now, we also understood that how to get these numbers into the registers inside the microcontroller before I perform the addition, because I cannot perform the addition directly on the numbers stored in the memory, because all arithmetic operation I can perform only on the registers. That is a advantage of RISC architecture, because you can able to execute those instructions in a very quick time. So what we have to do is, first I'll be copying the value, that is an address of the location called nums into the R0 register. So then I'm getting into two registers, R1. So within the brackets, if I use any of the registers, that means that I am fetching. So what does it mean? That I am fetching the contents of memory location pointed by R0. So I'm using R0 as what? The pointer. So what do I get? 10, I'll be getting it. So similarly, LDR, R2, so then R0, comma, hash 4. So that is, I am getting the second number into memory location. So this is an offset. What I'm doing is R0, whatever the value is there, plus 4, I'm adding it. Why plus 4? Because the next number is available at this address plus 4. That means, so if the address is 0, 0, 1, 2, 3 is meant for what? 10. So the 4, 5, 6, 7 is meant for the 20. If I assume that nums is 0, 0. So that is why I given a plus 4. So I got both the numbers. Now I'll perform the addition. So when I perform the addition, always, you can use add yes if you want to see the flags. So I will store the answer in R3, R1 plus R2. So I got the answer. Now till this we have understood. So how to get the numbers from the code memory and how to add them. Now I want to store the answer. If I want to store the answer, can I store the answer? Can I store the answer in code memory? No, it's not possible. I can store the answer only in the RAM area. So to access the RAM area, there are two methods there. Either I can reserve the memory. I can declare area reset like this. I can declare area where I can give a name for my result location. I can store it. Or if I know the address, I can directly refer that address. I can store the answer. As I've explained you already, so in the target, there is an option called where is my starting address of RAM is provided here. See, this is a read-write memory area. So in this read-write memory area, what is the starting address? 400. Since I know the starting address, I can store that directly. So what I'll do is LDR R0. Now I will store the address directly. So equals, so what is address? 0x400. So I've just stored it. So here, what is that? I do not know the address, but I know the name of the memory location. Assembler who allocates the corresponding address, assembler while assembling allocate the actual address related to the nums. So it will be substituted, nums will be substituted by the actual address when the assembler completes its job. Whereas here, at the time of writing the program itself, I am very clear what is an address. That is why I am writing myself the address. So I can use this method to get the data from memory. If I know the name of the memory location, if I don't know the address, I can use this method. If I know the name address of the memory location, I can refer that directly here like this. So now I have to store the address. What is an instruction which is opposite of LDR? Where is my address? Address in R3 register. So store the contents of an R3 in a memory location pointed by R0. Now, so if you execute this instruction, the answer will be stored at this memory location. We will verify this one, whether does it work or any issues are there in this program. So this program is for what? So program to add two 32-bit numbers, two 32-bit numbers. So stored in code memory, stored in code memory. Now I'll compile my program. Is it audible?
Yes, sir. Yes, sir.
I compiled my program. Now I'll go to the no errors are there. I'll go to the debug. So what I'll do is, so I will have both the memory windows are there ready for me. If you don't have the memory window, what you have to do, you have to go to the view and then memory window is there. Click on the memory windows, both the windows. So that will appear here. Since already I've clicked it, the memory windows appear. So two windows are there for me. One memory window I'm using to look at my code memory. Now, where is the code stored? From 00 onwards. So this is my code. So this is the code of the program 1C00. These are all the program code is available here. And also at the end of this program, I have a data. You can see that 10 is data is there, 20 is there. So data is also stored at the end of the program. So what address? We will see that when we run the program. Now I'll execute the first instruction. Now, when I execute the first instruction, R0 is loaded with the address of the nums. Look at the R0. What is that? 1C. So 1C is the address where your nums is being represented. So what I'll do, now I'll type the 1C. Now I'll type the 1C in the memory window. So see that. Now the moment I type the address corresponding to the nums, I got my numbers. What are the numbers? 10,000 is the first number, Little Indian format. Next 20,000 is another number. So I have got two numbers which I have stored in the code memory. So that means that this data is stored in the code memory. So this gives a clarity for me that at the end of the program, my numbers are stored in the code memory. Now I'll get the two numbers into the R1, R2. Keep observing the R1, R2 here. So you got the first number 10. So then you got the second number 20. So I got both the number 10 and 20. Now I'm adding these two numbers with a yes. So flags also going to change, depends upon the numbers what I have it. So depends upon the numbers, the flags going to change. Now R1 plus R2 is nothing but what? 10 plus 20 is 30 because it's already in the memory hexadecimal format. So I'll execute it. Now what you got? R3 30 is there and the flags are not changed. That means that for these numbers, no flags got affected because the answer is not 0. The sign flag is not set. So overflow is not generated. Carry is not generated. That is why it's all becoming 00 only. Now, whatever the answer I have in within the ARM core, that is in R3 register, I move into memory which is outside the core. So which memory location I have to refer now? I have to refer 400 is a memory location because that is the RAM allocated for this chip. So now what is there? 00 is there. Now we'll execute this instruction. R3 will move to what? This area because store instruction is going to work. Now we'll execute two instructions. First get the R0, the pointer, then execute. Now see that 30,000 has been reached to the RAM area. So this is how you can use the RAM area and also code memory area to get the numbers and store the numbers. Hope this is clear, this program. Now we'll go to the next program. So now what I have to do is I have to add two 32-bit numbers. I have done it, but two 32-bit numbers was easy because single add instruction could able to handle the two 32 numbers at a single shot. But now if my size of the numbers increases, let's say I'll take 64-bit, the same logic we can apply to 128-bit, 256-bit. So when sometimes it's required to allocate large number of bits to represent a number when you have to represent large values. So when there is a requirement of adding two 64-bit numbers are there, how do you perform that one? Let us take two 64-bit numbers and their representation, we will see that. So I will take the numbers which are two 64-bit numbers. So look at these numbers. So first 64-bit number R1 and R2 I just represented here. Second 64-bit number R3 and R4. In the sense, the number whatever I have represented here cannot be represented in a single register. That is why I've used two registers to represent the number, 64-bit numbers. So R2 I'll be storing the LSB of the number. R1 I'll be storing MSB of the 64-bit number. So I'm dividing the 64-bit into two 32 bits. So first 32 bits will be called as LSB of a 64-bit number. Next 32 bits of the 64-bit number will be called as MSB of a 32-bit number. So I'll be storing those two parts of the 64-bit numbers in the two registers because I cannot represent them in a single register because all are 32-bit registers. Similarly, I got another number which is stored in register called R3 and R4. Now I'll perform the addition of these two numbers. When I perform the addition of these two numbers, I'll be getting a 64-bit result. So what I'm doing is I have to perform first addition of the LSB of a first 64-bit number, that is R2, what is there in R2. Then what is there in the R4, that is LSB of a second 64-bit number LSB. Whatever the answer I'll get, I'll be storing in the R6 register. Then I finish the part of the addition of two 64-bit numbers. Then I'll go to the other part. I will take the MSB of the 64-bit number, that is which is in R1. Then I'll add to the MSB of the second 64-bit number which is there in R3. And then I'll store the MSB of the 64-bit number addition in R5. Only thing you have to do, you have to take care here is whenever you add two numbers, 32-bit numbers, you get a carry. That carry to be considered in the next addition. So I can give a simple example in case of a decimal. Let's say I have, so 7, 8 is there, and then 8 and 6 is there. These are the two numbers. So now I want to add these two numbers. Then what I'll do is I will add the first 8 plus 6. So my answer is 4. So then what I'll do is I'll add the 7 and 8, and then I take the carry which is generated from the previous addition. So previous addition, how much is the carry generated? 1 is generated. Now what should I add it? 7 plus 8, that is 15, plus carry. That means that, so 16. So then if I get anything carry, so which will be there here as a carry. So that means that, so whenever I add first time the LSB digits of a number, you have to add only two numbers. Subsequent digits, that is after the LSB digits, next whatever the digits you have on the left side, that is till you reach an MSB digit, you are adding three things. What are the two things? The numbers, actual numbers, which you're supposed to add the two numbers. Along with that, you are also adding the carry from the previous. That means that this addition is a 3-number addition. So 2 numbers plus the carry from the previous digit. So same logic applicable to here also. Now you are adding here, first time you are adding only R2 plus R4. Second time you are adding what? R1, R3 plus carry whatever they generated from this one. That is why most of the microcontrollers in the assembly language instruction set, they provide two types of instruction. One is called add instruction, other is called add with a carry instruction, ADC we call this. Add means it will add only the two operands whatever you specify, that is two registers whatever you specify. Add C means what? Add with a carry means what? It will add the two registers whatever you specify in the instruction plus whatever the carry flag is been set by the previous addition instruction. So we should be very careful when you write a program, when I have to use this instruction, when I have to use this instruction. So let's start doing the program. Now what I'll do, first I will store the numbers. I will store the 64-bit numbers in the memory. Two 64-bit numbers I will take. So I will take the two 64-bit numbers. I will store at the end of my program. Value 1 is a first 64-bit number. What I have done is I've just taken 64-bit number. This is a sample 64-bit number I have taken. How many digits in a 32-bit number? We know that how many digits will have it. So for example, so 1, 2, 3, 4, 5, 6, 7, 8. So 8 digits will be there in a 32-bit number. Since it's a 64-bit number, another 8 digits comes into picture. So now what I have taken an example for a 64-bit number where the MSB I have taken BBBB. It can be any number. The LSB of a 64-bit number I have taken AAA. Similarly, another 64-bit number I have taken. This is, I will call as a value 2. So this is MSB of the another 64-bit number. This is an LSB. So this two numbers I'll be storing in a memory. Since I'll be using DCD to store a number, I cannot store with the DCD the complete 64-bit number. So what I have to do? So first 32-bit number I'll be storing. Then I'll be storing another 32-bit number, which is belongs both 32-bit number forms one 64-bit number. You should not think this is a different two numbers. They are two parts of a 164-bit number. So I'll say DCD. First I'll store BBB. Then I'll store AAA. I'll store it. Similarly, so I'll store the CCC and then FFF. So to value 1 represent 164-bit numbers. So I'm splitting as 32-bit. I'm storing it. Now I got the numbers stored in the memory below my program. Now I have to perform the addition. So to perform the addition, I have to get the numbers into what first? Into R2 and R4 first. That is, so LSBs I have to get into what? R2, R4. I have to perform the addition. So I'll get those two numbers into memory. First, I will get all the numbers into my program. Look at this. So value 1 is an address. I'll just load into R0 as a pointer. Now I will get the BBB into the R1 register. So then R0 plus 4, that is AAA, I will get into R2 register. So now R2 contains AAA, R0 contains BBB. That means that you can look at here. R2 should contain what? AAA value. R1 contains BBB. So that I got the first number. So I finished first number getting into R1 and R2. Now the same thing I'll repeat for another number which will be stored in what? R3 and R4. R4 get FFF, R3 gets CCC. So now I have finished loading of the two numbers into the registers R1, R2 and R3, 4. I'll perform the first addition. What is the first addition? R2 and R4. So since I am adding only two numbers, I don't use add with a carry. I'll use only add instruction. So I've used add. Only thing is, it's very, very important. If I don't say yes, the carry flag will not be set. And the next addition, when you perform with an ADC, your answer will be wrong. You can verify that. It is very important that you have to make it a yes is important, because otherwise flags will not be reflected and your answer will be wrong. Answer will be only partially correct. So I'll say add s. Now what is add s? We'll do it R2 plus R4, keeping the answer in R6. So I finished my execution. Now I'll do the other portion. What does I have to do? R1, R3 plus a carry. So I will do the other addition. Now look at the other addition. So what is the other addition I'm doing? R1 plus R3 with a carry. So ADC R1, R3 with a carry. And where is my answer stored? In R5 stored. Now I have to store the result. For storing the result, we will use a different technique now. In the previous case, what I have done is I have explicitly used 0x400 and stored the answer. Now there is also possibilities there. You can use area directive and reserve the space in the RAM also. How do you reserve the space in the RAM area? This is the reserving the space in the code area. So now what we'll do before end. So now what I'll do before end, I will declare some area. I will declare an area here where the storage will be in the RAM area, not in the code area. So I will initialize that space. So now I'll go to here. I'll just enter. Now look at here for a moment. So what is I have done? So I have initialized using a area directive, memory space, which in which area? Data memory area, in the RAM area. Now, DCD is the directive used to allocate a memory in the code memory in terms of what? The words or double words like that. So space is the directive which is used to allocate a space in terms of bytes in the data memory area. So in the RAM area, how do you allocate a space? By using a directive called space. So when I say space, whatever the number you indicate, it should be in terms of bytes. Now, how many bytes are required to store my answer now? So we know that 4 bytes are required to store one 32-bit number. For 64-bit number, how many bytes are required? 8 bytes are required. That is why I'm reserving 8 bytes to store my answer. So what is the name of the memory where I'm storing my answer? I've just given as a result. Now I use this concept to store my answer. So how do you do? First set up the pointer. Let LDR R0 is equal to result. Now R0 will be loaded with an address corresponding to result memory location, which is dedicated, which is reserved in RAM area. Now, so my answer is in what? Two portions. First is R5 and then the R6. First I'll store R5 and R6 is there. So I'll be storing the R5 first, R5, and then I'll be storing the R6. So store the R5 in the memory location pointed by R0. Store the other part of the answer, that is an R6 in the next 4 bytes. That is why I given a 4. So now I finished my program. We will verify how this program will work. Also, we will add these two numbers in the calculator also. We will see that whether we get the same answer. So I'll compile this program. Am I audible?
Yes, sir.
Okay. So now I will run this program. Now I'll run this program. So before I'll verify both the memories, whatever there here. So this is 400 is a place where I have to store my numbers. This 40 is a place where I have to store my numbers. So before that, I will load the numbers into the registers. That is, so what are the registers I have to use? So these are the registers. So R1, R2, R3, R4. So I will execute the instruction till the first addition. Now I finish all the loading. Just verify whether numbers are there or not. R1, R2. R1 is BBB, R2 is AAA. So that is a expected number here. Yeah, we got it. Next. So what are the other register? R3 and R4 should get the second number. So look at that. R3 CCC is there. R4 FFF is there. That means that whatever the numbers I have stored, I got into the registers. Verify that first properly. Then I'll perform the addition. When I perform the addition, whether the answer is correct or not, either you have to do manually, take the paper and pen, you have to do the addition and find out, or you can use a calculator. So I will just invoke a calculator, which is already there. So I will share the whole screen. Now I will take the numbers, two numbers, I'll perform the addition. So what are the two numbers I have taken? So look at here. I have selected hex mode. In the hex mode, I typed BBBBAA and then the CCCF. You can see that. So these are the two numbers, BBBA and CC. So in the hex mode, I typed these numbers. I have done the addition. Say equals. When I did addition of these two numbers, this is the answer. I got it. So this is a MSB of the 64-bit number. This is the LSB of a 64-bit number. We will verify whether we get this answer or not. Now what we do is, so we will verify now. We'll execute the add S. When I say add S, the result should come in R6. What is the result you're supposed to get? AAA and AAA9. Now look at R6 now. Keep looking at the R6. Now we'll execute this instruction. So what you got? AAA, A9. So this is the answer. I have got it. See that? AAA, A9. So partial answer is correct. Then I will add another two other 32-bit numbers. That is MSB portion of the 264-bit number. ADC with a carry. I'll do it. Look at the carry flag also. So carry flag is set. See, whenever you added the first two 32 numbers, that is AA and FFF, the carry flag is being set. So that carry flag is being taken into consideration now when you do the ADC instruction. Now when you perform ADC, R1 is added, R3 is added, plus whatever the carry is there, that is also added to these two numbers. So now I'll perform the addition. Now see that what is the result you got in R5 after this one. So verify in your calculator, 8888. So R5 contains 88. That means that my answer is correct. What is there in the R5 is a correct answer. Now I want to store my answer in a result location. So what is the result location? Result location is what? 400. So I will verify this. See that the moment I execute the instruction, this instruction. So see that R0 has got a result 400. Even though I have not indicated anywhere in the program 400 for this data memory area, automatically the assembler allocated what memory? 40 is allocated memory for result. That means that automatically, since the chip is being already specified, whenever you declare this area, it starts storing, it starts allocating the space for the variables in this area from where? 4000. Even though I have not indicated, it is taken 400. Now 400 is a place where you have to store my answer. So what is my answer? Answer is in which register? Answer is in two parts of the register. One is in R6, it is there. R5 is there, you have to store it. So I'll execute now the two instructions. Now look at that. 888 is the answer. Look at that answer also with reference to my calculator. So 888, it is there in the first 4 bytes. Then AAA9 is there in the next 4 bytes. Since every 4 byte is stored in a Little Indian format, first A9 will be stored, then AAA, then AAA. Here it's all 888, that's why you cannot notice it. And the second number, since it's a different number, the digits are different in the Little Indian format, this 32-bit number will be stored. So this is my complete answer. So this is how you can able to write a program to perform the addition of 32-bit number and two 64-bit numbers. So there's always one hint is there. Whenever you want to add the two numbers, so you want to give the data dynamically, yes or no, you can allocate the numbers value 1 and value 2 in the data memory area itself. If you allocate the numbers in the data memory area, you can start using 400 as the reference for your numbers in the memory in the program, and you can feed the numbers at the runtime. So at the runtime only I can execute it. I'll just show you that one, how I can do that one. So for example, if you want to take value 1, instead of value 1, I want to store my number in 400. What you can do is you can replace the value 1 by 0x4000. Now, so what you have to do is at the runtime, you have to go to the 0x400, double click on this number, and you have to store the number. So you can change anything here. So you can change anything in the data memory. Say now it is changed. So that means that if you take the numbers from the RAM area, at the runtime, I can able to allocate the numbers. What is an advantage of allocating the numbers in the RAM area is what? You need not recompile the program every time you change the program. You can just see the left side. You can just reset your program. You can stop execution. So you need not compile also. So now what I'll do is I'll say debug. Now whatever the numbers required, I'll feed the numbers here. I'll enter the numbers here. So I have to enter the numbers here, whatever the beginning of a program. So whatever the numbers you require it. So let's say I've given some numbers randomly here. Then what I'll do is after entering all my numbers, whatever required, then I'll say what? So I'll start executing the program. So since you're feeding the numbers at the runtime, so the values you can feed to the program while you are running the program. Advantage is if you want to change the, again, I want to run the program for other set of numbers, what I have to do is I just reset my program. I don't stop my compilation. I just reset. When you reset, see that what will happen? Your cursor has come to here. That means program counter has become 00. Now go here, change the number. Now go here and change the number, other set of numbers. Then again execute your program. So your program also you can execute all at a single shot. You don't have to go to the step by step also. You can see that there is what is called, there's an option called run. F5 is there. That means that whole program you can execute in single shot. See that you can execute and then you can say stop. So then what will happen? Cursor come to the last statement. So you not execute a single step also. So advantage of using this method is what? Every time you change the numbers, reset and run your program, check your result. So you need not recompile the program for feeding the new numbers. This is one method. So whenever possible for 32-bit numbers, you can try this method. So this completes the session on the first two programs for 32-bit numbers, 64-bit numbers. So what we have done.